Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks.
Welcome back, and this video is the first of two looking at maximum demand and diversity. Now we're going to do understanding demand with this video, and we'll do an application of diversity and stuff in the next one. From my experience, quite a lot, especially with electrical inspection, condition reports and such, a lot of the time the maximum demand just gets left alone, or it's empty, or sometimes the size of the service fuse is there, or there's a random number, and it's very hard for people to advise on it because it is really a figure that's based on judgment. There is guidance in the on-site guide through to the design guide, which we're going to use in these two videos, and they're the best thing to use if you have no clue what to do. Some other people have the idea of adding up and then dividing by the number, and they get a random number that sometimes works. But it has to be a realistic figure. But what you're doing really is you're trying to get an understanding on how much pull the electrical installation wants, how much demand it wants. So if you have a service fuse, that's how much it can have, not how much it wants. We're not going to worry about diversity in this video, so we're just looking at how electrical equipment behaves and understanding what it's doing when it's doing it. So we'll start off by just talking about the simple lamp, the simple incandescent lamp, although they're becoming a bit prehistoric now. So a good understanding is the assessment of demand is considering how much current is taken by the circuit over a period of time. That could be half an hour, could be a shift. It depends on your assessment. You know, it could be a school day. What are you assessing? What part of the installation are you assessing? It's always good to assess the demand when it's fullest, though, because the fullest demand has to be tolerated by the installation. In the case of something like an incandescent bulb, though, it may have low wattage, which works to about 0.43 amp, but it's full demand. It's incandescent, so when it's in operation, it's pulling fully, and then when you turn it off, it stops pulling. That's how the demand of a lamp works. Now, if we move that over to something else that's a little bit more sophisticated, like a washing machine, that doesn't have a constant demand. It has a variable demand depending on the point of work. So you'll have a variable speed motor that's going to be obviously doing lots of driving the drum around, rinsing. You'll have a pump, and you'll also have a water heater, especially if it's a cold-fed one, which most of them are these days, I think, that come into the domestics. So you're going to have different processes. You're going to have obviously heating up the water for the initial wash. You're going to have rotating and washing, and then you're going to have more power as it does aggressive spins. And so from the time that you press on to the time that the machine has finished, it's going to have different amounts of power demand through that process, and that will look a little bit like this. So you've got the initial startup. You can see we've got here's the load in amps. So it's a 2.5 kilowatt washing machine. So there's its peak demand there, and that's going to be when it's doing its heating and washing. We all know that things that heat up will pull more draw. But once it's done its initial wash, it's then going to just slush it around, spin it with a little bit more power as it uses the motors more aggressively, rinse it and spin it. So you can see the biggest demand is at the beginning. So if you have two washing machines in your kitchen, don't turn them on at the same time. Turn one on, and then if you have to go out, wait until it's about to start the second half of it, turn the other one on. This is what understanding demand is about. Applying the equipment at pivotal points in electrical demand. Now let's assume that we have another appliance in the kitchen, such as a tumble dryer. A tumble dryer doesn't have cycles of rinsing and spinning and washing. It's drying, so it's just full. It's demand is full throughout its process until it wells down at the end. So you come to understand why a lot of these fires start from washing machines and tumble dryers, especially when they're under excessive load and they're not well maintained, because they're on full constant demand, these tumble dryers. Yeah, so if you have a washing machine and a tumble, when the washing machine is starting up, maybe don't put the tumble dryer on first. Wait with the tumble dryer. So you can assess with your demand if the client uses the installation this way. If it's a domestic, then it's probably going to be a washer dryer. If they have a washer and a dryer, you can just get an understanding of that, or you can just add them up. Not a problem. But if they have overloading of the circuit, it might be that they're putting them on simultaneously. And bearing in mind, they may have a dishwasher as well, which again heats up to wash, 10 amps to heat it up, washing it for a 2.5 kilowatt heater in there. A cold rinse, don't need much electricity for that to heat that up. It's a cold rinse, and then a hot rinse, more power. So you've got to understand how they use power. Now these are 3 appliances that go on for a number of hours, but then we'll also have the ones in the middle in the kitchen as well. We'll have the kettle and the toaster. Don't have too much effect if they're used for short duration, because their demand, whilst being considerate, isn't for long. And we're looking at probably up towards an hour for a conductor to reach optimal operating temperature under load. So it's not too much of a concern, but if you have them being used all together at the same time, regularly, consecutively, you need to consider the overall demand. And again, in that real world, you may be looking at more of the water urns or the water boilers instead of just the kettles. But you need to consider their use, consider their demand. Let's combine these things that we've just looked at then. So we've just looked at washing machine, tumble, dishwasher. So that's one appliance at 10 amp, another one at the startup, and then kettles later on. So let's think about how that adds up to a single demand for a circuit. There. So we've got initially for the first hour or so, or for the first half an hour, 30 amp. Yeah. And then for another half an hour, because obviously the tumble's finished, I guess. Sorry, that's just the tumble. The washing machine is doing cold washing. The dishwasher is on cold rinse. It's just the tumble dryer that's working right now. And then you have the hot rinse to combine with that. So you can see how the patterns change through a 2-hour cycle. But this is what the demand is. It's the point where they are all doing their most work. And that is what you've got to figure out. Okay? And again, it's not a case of adding the total power up if they're used in a way that their total power isn't used at the same time as other appliances or other pieces of electrical equipment. Okay? So, even in a simple installation such as a house, there are many loads. Not all the loads run at the same time. The loads are diverse. This is where diversity starts to come into it. Okay? They're diverse in their current demand, control mechanisms, and the times of use. Okay? This load's diversity results in the total load rarely equaling the sum of the individual loads. As I said, the biggest concern is if like the kids have just got dropped off at school, and she comes home or he comes home, and he puts the washing machine on, puts the dryer on, gets the dishwasher going, all at the same time. That's where we have these big demands. But most likely, it's not a problem. But again, in industry, same issues. Yeah, where we have all the demands on at one time. This is why with your electrical design it's important to understand the working environment, but also the working conditions of the electrical system. Okay, you can have a factory that's got electrical equipment, and you've got to understand how it's going to pull, how the electrical demand will work on that electrical equipment, so you can make sure that the equipment supplying its distribution is adequate. Okay. So cables and other equipment's maximum capability is limited by the temperature. We know this. So thermoplastic typically will be 70 degrees, thermosetting 90 degrees, unless obviously you've got a different cable of 60 or whatever respectively. And the current carrying capacity are to those ratings. Short time high current demands may be acceptable, such as kettles. This is an interesting point. If you look at a kettle such as even the Comet kettle you may have at home, it might be a 3 kilowatt kettle. That'll pull, 13 amp. But you may notice the cable feeding it is only 0.75 mil, which the code of practice will tell you won't carry that much. Some manufacturers will deliberately put in a smaller cable to the electrical equipment, because the electrical equipment is designed to be used for very short duration. A kettle, for example, is going to have a rapid boil 3 or 4 minutes, so it's designed to pull current that exceeds the current carrying capability of the conductor, but being a short duration, it's not considered to have any thermal effect due to the fact that the conductor is not going to build up to a temperature within the short time frame it's under load. So you may experience that. What you need to do is assess if the use of the equipment is suited to the manufacturer's expectation. If the person who's bought this kettle is actually running some kind of cafe and is using the kettle regularly, so it's not actually, she's turning it on or he's turning it on after it's boiled every time, the conductor isn't being allowed to cool down and it will be overloaded. And again, that's where they're going to want to swap them out for them those water urns, which you'll notice will have the thicker 2.5 mil cord set, or maybe even be on a 16 amp plug. Okay. This consideration of the different way the system is used can result in a complicated demand pattern. It requires listening and talking to the client to understand how the system is going to be used. Peek at diversity. We're going to cover diversity again in the next video, but here's a little introduction to how it works. So this is the allowance made for circuits themselves that would not always be turned on at the same time. So you can have XYZ circuits, but then they may not be on full power demand. Now, this illustration, for example, any one particular ring final circuit is unlikely that every socket outlet will have a load plugged into it. That's right. If you think about what you've got at home, you may have stuff left plugged in, but they're probably not under full load, and things that probably are under, they're negligible demands. There's an illustration here that is from the old B&B training that I used to use, and it came with a box saying this is unlikely to happen even on the coldest day. Now, I've added the words, but it still can, because I actually have seen this happen. When I was working at a race course, there was a flat that had been converted to an office for the, I think they were the cleaning company. And it was down at the old cold bottom of the race course. And it was just a domestic 3036 fuse board wired up for a flat on a ring final. Because it was cold and there was no other heating, they just plugged in 5 or 6 of these convector heaters all into a single circuit. Now, it didn't actually damage the final circuit itself, but what it actually did do is it overheated and overloaded the distribution cable to the board that was feeding that flat. And when I went to actually do an inspection, I can't remember what I was doing. I think I was doing a check on the current being pulled on the conductors, and I put my my mega current clamp meter onto this cable, and it was something like I think it was a 63 amp MCB, but it was pulling well over 96 amp. And whilst I was kind of just jotting things down and not keeping an eye on things, my actual clamp meter, the plastic around the jaws had melted. That's how hot the cable was. I was under this load because I just overloaded it. But being 3036s, the fuses downstream, they weren't ready to blow. So the MCBs upstream, or the distribution to the board was tripping first. So there was a very poor discrimination on that. So this can happen. It shouldn't, but it can. Right. Now, one good example of diversity is the cable that feeds the feeder pillar down the bottom of your street. You got the supply company, the DNO. They've obviously got to put cables into the ground to feed the feeder pillars, and they've got cables to feed your houses. Now, if they assume that your house, your house and your next door neighbour's house was all going to pull 100, 125 amp, they'd have to add them all together, and they'd have to then put in a huge cable. But they apply diversity. They consider that you may feed a supply to a row of 5 houses off of a feeder pillar, but the people in these houses live and behave differently. So, for example, these are all the same size houses, but you may have people who are just buying new houses, or you may have people who just live alone. So let's just play this example. Let's say we have one person living alone. Think about what kind of electrical demand there's going to be, what kind of behaviour will there be. So during the daytime, there's going to be little to no electrical demand because they'll probably be at work, unless they work nights. They'll come home, probably won't fancy putting on the big electric oven. They'll probably just put something in the microwave, dinner for one kind of thing. They may even get takeaway. So there's not a big electrical demand there. A quick shower before bed, laundry days at the weekends, really, because there's not a lot of laundry building up. So from an electrical demand perspective, not a lot. Now, obviously, this guy, gets lucky, falls in love, moves her in. Now, you may have 2 people working. You might now start using the oven. A couple of days a week. You may actually have a couple of showers now. You want to smell nicer, more electrical demand. Laundry days probably still at the weekends, maybe twice a week, but there's a slight increase in electrical demand. And then magic happens, this kind of thing. Suddenly, there's electrical demand during the daytime. Now, there may be a little bit of electric used in the morning. You're going to have some use in the daytime. You'll have oven cooked dinners. God forbid we microwave cook, when we feed our kids these days. Routine showers and laundry, a couple of days a week now. And you see the trend. Now, then you get to my situation. Because I have a wife and 4 boys. So, we have me away at work, stay at home, oven cooked lunches quite regularly, oven dinners every day, showers go all the time, baths, laundry 2 or 3 times a day. So washing machine, tumble dryer, dishwasher all day long. So this is what diversity looks like when we feed a supply to a number of units, but we consider the use of those units to be different, the demand of electricity to be different. That allows us to compensate and decrease the supply to it. This is what it looks like on a trend. So you can see here, we got the light green line here. Here's the electrical demand over a 24-hour period. So you've got your midnight, you've got your 4 a.m. Here's morning time. A bit of toast maybe, and off to work. Come in, a bit of Xbox, bit of TV, maybe a microwave, dinner, shower, bed. This is for 2. Bit extra effort in the mornings maybe an oven cooked dinner. And then you can see we've got the big families. We've got a lot of demand in the morning, showers, probably the oven, then progressing through the day, washing, tumble drying, laundry, and then dinner time, and then the gradual showers before bed and all that stuff. You can understand what diversity is about, and this is a domestic example of diversity. In industry it is similar. So what you do is you say, right, I'll supply that unit and I'll supply that unit, and you give them a maximum power demand. But if you then had within that unit, you had 3 or 4 hoists, and you had mechanics in the mechanic garage, and they had to use them all, and they're all operating at the same time, you'd apply no demand. If, however, they would use that machine or the hoist, you can then apply demand that won't be on when that is on. I'm saying machine, I ain't got a clue what it would be, but you know what I mean. So you consider the use and the work patterns of the environment, and that's how demand and diversity works. Now what we're going to do in our next video is apply a bit of this to some sample installations, a small office maybe, or a little workshop. We'll have a number of light circuits, and what I'm going to do is I'm going to stick to using the information in guidance note, on-site guide, but I'll also go to the electrician's design guide, But I'll probably change some of the numbers just to make it a little bit different. But that's what we'll do in the next video. We'll close this video here. This is just introduced the idea of demand. Okay, and then we'll do another one, and we'll look at what diversity is.